All right, we can go ahead and get started. I'm not going to speak for too long, but hello, happy Friday, happy almost the weekend. Hope that everyone has something fun planned for today to end the week strong. I'm going to turn it over to Emine, who is going to introduce our talk today. We will be hearing about relations between problem difficulty and problem format.
Thank you so much. Great. I will start sharing my screen because I have an introduction slide. Are you seeing it all right? Okay, great. Hi everyone, my name is Emine Simsek, and in this presentation, in this symposium, we will be talking about relations between problem format and the problem difficulty, so students' problem solving performances. And I will give the first presentation, and it will be about the relationship between problem features and problem solving performance for equivalence problems. Then I will give the floor to Verena, and she will be talking about different features of problems, and she will be talking about the relationship between these features like place value, carry-barrow procedure, and how students solve, how this affects students' word problem solving performance on word problems and arithmetic problems. Then Gabriella, Daroczy will be talking about the same question, but she will be talking about different studies which use different methodologies. And lastly, we will hear from Sarah Powell, and she will talk about, again, different features and how these features relate to problem-solving performance. And she will be talking about the role of different schemes and the position of the unknown. And yeah, I will start my presentation. As I said before, my name is Emine Simsek. I am currently working in Turkey in the Ministry of Education as an education expert, and I did my PhD and worked as a postdoctoral researcher for 1 year at Loughborough University, and this study was part of my PhD. I will first give a little background about the study and students' understanding of mathematical equivalence. And much research shown that equivalence is a key concept in mathematics, and we know that understanding mathematical equivalence relate to students' further mathematics performance, their arithmetic and algebra performance. However, it's also has been shown many times that students have difficulty understanding this key concept and defining the equal sign relationally and solving equivalence problems. What I mean by equivalence problems in this presentation are equations which have operations on both sides, and usually one of the operands is missing. You can see an example here in this slide. Students' conceptions of the equal sign is well documented. We know that some students have the operational conception of the equal sign, and they tend to define the equal sign as do something symbol, or they say equal sign means this answer. But we expect students to have a relational understanding of the equal sign. We want them to define equal sign as the same, or we expect them to know that two sides of the equal sign can be swapped. There are some strategies that students use to solve equivalence problems. Two of them are incorrect, and below two of them are correct. So as you can see from the first strategy, some students ignore the second part of the equations, so the part after the equal sign, and they only use the numbers before the equal sign. Or some students, especially those who have the the operational meaning of the equal sign, ignore the position of the equal sign or the unknown, and they use all the numbers and operations at the same time, and they reach an incorrect answer. But we expect students to solve correctly this problem, to use correct relational strategies. And for this, some students make the calculation, or some students look at the relations between numbers and operations, and they reach the correct answer without the need for calculation. And in my PhD, I used a mathematical equivalence assessment, and I asked a few equivalence questions to students, and I noticed that same students become one student solve one question operationally, but then they become suddenly relational for another equivalence questions. So this make me think that maybe some features of equivalence problems make students change between strategies, between operational and relational ones, or maybe even between relational strategies themselves. So I checked the literature, and I've seen that there are quite many studies looking at whether there is a relationship between problem features and problem solving performance for traditional arithmetic problems. What I mean by traditional arithmetic problem is equations which have operations only before the equal sign. You can see an example here. And research has shown that problem size, position of the unknown, presence, absence of a borrow procedure, the type and the number of operations, use of compensation strategies. These are the features that relate to problem difficulty and students' traditional arithmetic problem solving performance. But the same question for equivalence problems is not really investigated so far. And I've came across this paper written by Homburg and her colleague. And this study also highlights that to date, there is no research has directly examined this relationship between problem features and problem solving performance for equivalence problems. But in this research, Homburg and her colleagues looked at whether left blank formats are more difficult to solve compared to the right blank format. So left blank format means equivalence problems, they have the unknown after the equal sign on the left, and right blank problems, equations which have the unknown after the equal sign on the left. And they found that the left blank problems were actually more difficult for students or primary students to solve. They did a meta-analysis to answer their research questions, and they reached this conclusion. Except for this study, there is another study looking at a similar question, and they found that equivalence problems involving commutativity property of the addition are easier to solve for primary students. But except for these two studies, there is not a systematic research study looking this problem. And I wonder, after reading this, children whether this result can be replicated, whether children are really more found left blank problems more difficult compared to the right blank problems. Also, I wonder whether other problem features like problem size, position of the unknown relative to the equal sign matters, whether they influence problem difficulty. So we design a study, look at this question, which features of equivalence problems associate with problem solving performance, and we identified three features. The first one is position of unknown relative to the equal sign, whether unknown being after or before the equal sign matters. and position of unknown within the expression, unknown being on the left or on the left in the expression matters, and use of shortcut. As you can see from the example here, some equivalence problems are easier to solve by using shortcuts. As you can see, you can have a look at the relations between numbers. They are too close and you don't need to make the calculation here. And maybe this, we thought that maybe this can make students to change strategies and use a different strategy. So this was one of our features. And I will be presenting the results from the pilot study. I was really hoping to present the results from primary students, but my data collection didn't go well because of COVID and study being online, but we are still trying to recruit primary students to do this study with them. But I will be presenting results from the adults today. We recruited 140 adults to answer our research questions, and they answered two-digit equivalence problems, which involved only addition as an operation. You see an example here. And problems were presented on a laptop computer using Psychopy software. And we gave 7 seconds for each problem to adults. We manipulated the 3 features and to create our problems, and we came up with 8 different formats to have a look at. As you can see, first we have unknown after, unknown before the equal sign problems. Then for each of these, we have left blank, right blank problems, and for each of these, we have shortcut and non-shortcut problems. You can see some examples here, and we look at adults solve these types of problems, and when we looked at the difference between their performance between these formats. And this was a pre-registered study, and we did a 2x2 repeated measures ANOVA. We have results from both accuracy and response times, and they are quite similar. And in this presentation, I will be talking about accuracy results. And our results demonstrated main effect of shortcuts, but neither of the other 2 factors, position in relation to the equal sign or position within the expression, had main effects on accuracy. And we found a significant two-way interaction, position within the expression. And further, a simple effect analysis demonstrated that, and this was significant both for shortcut and non-shortcut problems. And as you can see here, for non-shortcut problems, right blank problems were more easier, so they struggle with left blank problems. This was expected based on Homburg and her colleagues' study, but the result for shortcut problems was a bit surprising for us because they found left blank problems were easier. So we tried to explain this. We looked at the literature, but we couldn't find anything. So we go back to our design and check the problems again, and we suspected that there might be a confound of problem size effect. Actually, we thought that we used a specific range of problems, but after controlling, we noticed that the mean of the correct answers on the left blank shortcut problems were smaller than the right blank shortcut problems. So, and we thought maybe this can explain things, but still we are not sure. And for sure, we can say that the participants were more accurate and quicker at shortcut problems. We couldn't really talk about the position of the unknown related to the equal sign or within the expression. But this confirms that problems being solvable with a shortcut potentially had an effect on strategy choice and thus accuracy and response time. So adults were successful at identifying these shortcuts, and they really used these shortcuts. And now, as I said, we are doing this study with primary students, and hopefully this time we design the study better. And I believe this study is important because we need good measures of understanding of equivalence, because it's a key concept, and much research try to grasp students' understanding of equivalence. And if we know that which features are related to performance, we can manipulate these features to create better measures. And this is quite a novel study, as I said. There is not much research looking at this question systematically, and I believe that teachers will benefit from knowing that which format students are likely to find most difficult or easier. I think this is end of my presentation, and I can take maybe one quick question. Martha?
Hi, thank you for this lovely talk. Really interesting data and findings. I have a question about why you see this reversal for the shortcut problems. And I wonder whether there is a difference in the salience of the number relationship depending on the position of the numbers. So to do the shortcut, you need to notice that 18 and 19 are just one apart in your example. And I presume that they were just one or two apart in most of the other examples as well. It might be easier to sort of see that quickly. It might be quicker to see that depending on the distance between those two items. And maybe, you know, if one is at the end or something, it makes it more salient. So do you think it could be a perceptual thing that helps highlight the shortcut relation?
Yeah, I think this is a really good question, and I didn't really think about this, but I think we created all the problems in the same way. I think there were just one or two differences between the numbers, and the position were really similar. So if maybe you are right, and maybe there might be something perceptual, and if we change the position of those two, the results can change. So I think this is something we need to look at too. Thank you so much.
Yes, thank you.
I don't think there is another question.
I have a quick question. Did you have speeded conditions where the adults were solving this, like the shortcut and the non-shortcut problems? Was there a time limit?
Yeah, they for all of the problems, they had 7 seconds. It was the same for all of them. Yeah.
Interesting.
They didn't
I wonder maybe like manipulating, you know, even a shorter time limit, and then maybe that connection, like Martha said, with the perceptual piece. I'll put a paper in the chat as well that relates to that perceptual piece. I think it's really interesting.
Okay. Thank you. Thank you so much. I'll give the floor to Verena, if that's okay. Verena, are you here?
Thank you.
Okay, yeah. So
Fine. So I'll share my presentation.
Perfect.
Okay. Yes. Today I would like to talk about one of my studies for my PhD thesis. And yeah, it's about effects of place value and magnitude processing in word problem solving. And yeah, it's with Corbinian Möller, who is my PhD supervisor. Okay. Yeah, mathematical textbooks provide plenty of word problems to exercise and to deepen previously learned mathematical knowledge, and as well to foster problem-solving skills. And so word problems are widely used in math instruction to help bridging the gap between classroom and everyday life situations by presenting arithmetic procedures within context of everyday situations. However, bridging this gap does not seem to be easy for students and often leads to problems in school. Typically, word problem consists of a short text describing a situation with quantities given and a question based on the presented problem. So word problem solving requires integration of verbal and numerical information into a mental model of the problem. Accordingly, both verbal as well as numerical factors account for the difficulty. Although word problems in the end require to solve an arithmetic problem, there's little research so far regarding influences of basic numerical processes on the difficulty of problems. Instead, most research focused thus far on linguistic aspects, the use of pictures, the underlying mental model, and so on. And we focused on influences of place value processing reflected by the carry or borrowing effect and the problem size effect. Our research question was set out to evaluate effects of presentation format, word problems versus problems in digital Arabic format. And we set out to evaluate demands on arithmetic operations, place value, and magnitude processing to better understand the complexity of word problems and motivate teachers to consider these factors in mathematics instructions. Our study, we had 128 students from 3rd grade with a mean age around 8. And we had 32 math problems presented as a word problem and in digital Arabic format. In some, we had 64 items. We manipulated presentation format, arithmetic operation, problem size, and if the problems needed a carry or borrowing operation or not. You see on the right-hand side an example for the word problems and underneath an example for the digital Arabic format. Our results showed that we found main effects for all factors: presentation format, arithmetic operation, problem size, and the carry borrowing factor. But we were especially interested in the interactions for the presentation format, and we found a significant interaction between presentation format and arithmetic operation. The difference between addition and subtraction were larger for word problems. We found as well a significant interaction between presentation format and carry borrowing and the carry borrowing operation, indicating that reaction times and as well as error rates were more pronounced for word problems. And we found marginally significant interaction between presentation format and problem size, as well with problems with a large operation with a large problem size were higher in word problems. Additionally, the three-way interaction between presentation format, carry borrowing operation, and problem size was as well significant, and meaning that the effects we found in the two-way interaction were broken down from them. We had significant effects also for the digital Arabic format, but they were stronger in the word problem format. The ANOVAs for the error rates indicated similar results as we found for the reaction times. Yeah, our results indicate that word problems are more difficult to solve in terms of reaction times and error rates, and they pose significantly increased demands on arithmetic operation, place value, as well as magnitude processing in the way that the effects were elevated in the word problem format. Also basic numerical processes play a crucial role for word problem solving. And this means word problems are not just another framing for a specific arithmetic problem. They are numerical and arithmetic processes are interwoven with written presentation, which seems to specifically increase the difficulty of these problems. And so it may be that word problems are a really qualitatively distinct kind of arithmetic problem, requiring other and different solutions strategies in addition, and to finally calculate the derived arithmetic problem at the end. Yeah, to sum up, numerical effects seem to be more demanding to children when put into a text problem. And this is what teachers need to know, that it's not only posing, presenting another type of problem for the children with the same difficulties like in digital Arabic format. No, it seems to be more difficult when put in the text problem. Yeah, that's it. And yeah, these are my colleagues, Silvia Pixner, Isabella Kreilinger, and Christina Kraut, who work with me and worked as well on this study with me. Thanks. So I'm just... Yeah, and the idea for the study we had when reading the article from Gabriella, yeah, who gave us very interesting insights.
We can have a couple of quick questions. Verena, if that's okay.
Yeah, sure.
Hans, do you want to?
Yeah.
Okay.
I can start. Interesting talk, thanks. Verena, I have one question as regards the design of the word problems. Did you control or manipulate lexical consistency? Because, you know, some words are associated with addition like to, and others subtractions like to get or to give away or so. And I'm asking that because in some of Gabriella's studies, sometimes we found, don't know if you talk about it today, but sometimes we found that actually operation effect interacts with lexical consistency. So when you basically would find it larger in the word problems and in the Arabic digit problems, it would only be for certain designs of word problems, I think more for the lexical consistent ones and not so much for the lexically inconsistent ones.
Yeah, yeah. we looked in all of these problems which are associated with lexical problems, and tried to put them out of our design.
Counterbalances or control for it. Okay, yeah. So half of your problems were consistent, half of them were inconsistent, or how did you do it?
No, we didn't have consistent or inconsistent. We didn't mix them. We
okay.
only had
consistent ones, probably.
Yeah.
Okay, yeah. So it's interesting. Probably. If you would replicate our results, when you never know that, of course, then you would only find what you find for the operation effect for consistent ones, but not for inconsistent ones.
No.
So, but it's nice when you had consistent ones, then it's in line with what we find, and we didn't compare it, but I should be bigger there, larger there. Yeah. Okay, thank you. Sorry.
And Elizabeth?
Yes, hello. Yeah, I would just like to ask you, and thank you first of all, Verena and Emine. Did any of you ever do a study at the same time, concurrent with the study on the word problem solving, on the reading competence of the participants? Because we found that it's not just linguistic and specific lexical issues or syntax issues, but that some people just don't read well and don't read with cohesion. And in word problems, often one statement follows the next one, and that the cohesion between the sentences, the connections are gone. Thank you.
Now, in this, we also did arithmetic tests and the reading tests, yeah, and we looked into our sample, and we had not really problems in the with children that didn't read good enough, and as well our students were also only German speaking.
Okay, Sie könnten dann alle lesen. Okay, thank you so much.
Mm-hmm. Maybe I could also add something to this point, because I will not present this. That as in reading, we had also some kind of test to see how reading comprehensions goes with strategies, and children who had better reading comprehensions did solve these problems quite differently. So, for example, they could vary more, they had more patterns, or they started with the question, so they could really read more goal-oriented, this question. So I think it counts a lot.
Okay, thank you so much. Our next speaker is Gabriella.
So I think it fits very well to Verena's topic. Let's see. And so, is it okay? Okay, fine. So, hi, I'm Gabriella Daroczy. I'm a postdoc at the University of Tübingen by Hans-Christoph Nöll. And I will present a series of studies which were part of my dissertation. So, first of all, the word problems are a key component of mathematical education since centuries. And according to the PISA, there is a problem because 1/3 of the students cannot even solve a simple problem containing basic algorithm and involving whole numbers. So it's not really fully understood why the arithmetic and the numerical changes alter the performance, the role of the numbers, and and what is the role of the numbers in the mental representation of the word problems. So to begin with, it's important to look at the process of the word problem solver. The existing models originate from the text comprehension theory from Kinch and Greenough, and this is a propositional theory where slowly the text determined the difficulty of the solution. And this model was extended later with the so-called mental model or the mathematical model, which is the mathematical representation of the text. And so there are several phrases like this first reading phrase, the integration planning phrase, and at the end, the calculation execution phrase. Of course, this is a very, very simplified model. And and the question is that if people just start reading, so according to this original model, they first read it and then understand the text and then they start calculating. So the calculation process should be separate from the mental models. However, there are other models which say that the people conduct a magnitude-based mental representation. So why does a simple change alter the performance? Where does the calculation takes place? To this, answer this question, we should also, I try to press this, we should also consider the textual difficulty of the problem. So because some mathematical factors cannot even divide it from the text, from the linguistic factors. And for that, we have introduced a distinction which has not been prominent so far, and this is so-called relatedness, where we distinguished related mathematical and unrelated linguistic factors, which means does this factor related to the other domains or not? So it's also easier to connect to several problem-solving phases. And the related and non-related factors might affect the problem-solving process at a different extent, even processed differently. So investigating the interaction between these factors could provide a further understanding of the problem-solving process. So it could also answer that the calculation, if the calculation process influences, for example, the mental model, it should interact with the related factors too. Now I will introduce all the factors we used in the studies and then give an overview of the studies. So like an unrelated factor would be the carry. It means you don't change the text, you can simply change the numbers and alter the difficulty of the text. And if so, it should affect more this calculation phase. And the second mathematical factor would be the operation. This is related to the text. This is related to the mathematics behind. You change the mathematical model. This is differentiation model also. And for regarding the linguistics models, this is the lexical consistency we have chosen because it's one of the most researched factors also. Here you have basically a keyword like earns, and you associate this word with the operation. This can be consistent or inconsistent. So if earn is a plus and you have to calculate plus, this is consistent. If you have to calculate subtraction, this is inconsistent. This is a factor which clearly affects the mental representation. If you go further, like the other linguistic factor is the nominalization. This is something where we also change only a small part of the text, like nominalization turns a verb into a noun, and it makes just more difficult to read. So this is something which should affect more the first part of the problem solving. And this is, and in all experimental studies, we manipulated this arithmetic and linguistic complexity independent and orthogonal. In the first study, we had 320 word problems. And here you can see an overview. And we investigated also children and adults because the results from adults are not necessarily transferable for children. And we also use eye tracking measures to understand the underlying processes. Not always, for example, the children study involves the eye tracking measures. And of course, the mental representation is hard to investigate at the behavior level. So there is also a near study where you can see the first picture. The analysis is not finished yet. Here we included only the operation and the lexical consistency. So then let's go to the results. First, the main effects for the carry-borrow. For this unrelated arithmetic factor, carry-borrow, it caused the greatest increase in solution time across the factors for the adults. Moreover, both adults and also the children experienced more failures when the word problem included the calculation, carry, and the borrow. Then For the eye movement, we didn't have this. For the operation, in case of the related factor operation, both adults and children needed more time for subtraction than for addition. And this direct effect of operation was also present in the eye movement data for the children. So I go also to the next slide. Here you can see parts of the eye movement analysis. So the numbers were affected by the changes in the eye movement measures. So there were more rereadings on the numbers, both numbers together in case of the subtraction compared to the addition. But there were also more rereadings on the text. So this part that you can see without the numbers in the case of the subtraction than the addition. And this hints that this kind of subtraction operation process is part of the mental model. So this is actually fine. And very interesting are the interactions. So first, the interactions of the related factors. We expected the related factors to interact because both of the factors are strongly connected to building these problem models, and operation and lexical consistency interacted both for adults and children. So the more difficult arithmetic operation led an extra process, extra demand on problem solving. And this interaction was stable across the studies. Also, for example, in a near study, we couldn't see on the behavioral level this interaction. However, on the level of the neuronal correlates, we could observe the consistency effect, for example, only for the addition and not the subtraction. Okay, and so another interesting part is like the nominalization and the operation. It suggested that the children made more errors when subtraction problems were involved compared to addition problems. So this can be interpreted that it's harder for the children to construct a good model when the language is more complicated. So, and the last one is the carry and the interaction with the other factors. So the presence of an interaction between this non-related arithmetic factor carry and the other factors may also answer if the computational processes affects the problem building phase or not. So for children, the consistency effect and the operation effects were both pronounced in the case of the carry compared to the non-carry, so more pronounced. And this means that for both consistency and operation, effects grow larger when the tasks involve complicated calculation, and then it's even more difficult to build a correct problem model. And so in children, it's not that separate as in adults, it seems. So some conclusion. So for adults, we hadn't seen this interaction between the related and the unrelated factors only for children. So it might mean that for children, this numerical information in text plays a bigger role for the word problem processing as it previously assumes. So, and some kind of future direction. So it would be more, so a stronger involvement of numerical cognition would be important in the word problem research. And I will also show for the last slide, next study, because of the eye tracking level, the carry was not included. There's the study I will present on the MCLS in June, hopefully. And we have a very slow sample size. And here, what we decided to manipulate is solvable and non-solvable problems. And for the non-solvable problems, you don't need the numbers. And here in this study, we manipulate also the carry and the non-carry. And the basic idea would be whether the people look more in the carry condition in the non-solvable problems than in the non-carry condition. And if it's so, then we could clearly see if the number processing is involved also in the earlier stages of the problem solving or not. The preliminary results show that might be the case, but it depends also on the condition of the problem. So it was seen only for the subtraction non-solvable problem, but not in the other conditions. And I think that it is, and thank you for your attention. So if there are some questions, I don't know if there is time.
I think we can have just one quick
One
question,
question.
if there is any. If not, I don't think there's any question now. So I'll give the floor to our final presenter, Sarah Powell.
All right, thank you so much. And I'm here with my amazing colleague, Tessa Arsenal, to talk to you about differences in word problem solving based on item characteristics. So I'm Sarah, I'm at the University of Texas at Austin with Tessa. And if you want to reach out and talk to us more about that, there's our contact information. So this study that we're going to tell you about has just come out in a journal called Learning Disabilities Research and Practice. And here we looked at these word problem differences by schema. And we really were interested in a comparison of students who experienced difficulty with math versus students who did not have math difficulty. And so across 3 years, we collected this data. This was part of an Institute of Education Sciences grant that we ran in grade 3. And so every year at the beginning of the year in September of our school year, we screened students for word problem difficulty. And as part of that screening process, we gave a word problem measure that focused on single-digit word problems. And then we also gave a double-digit word problem measure. We used that single-digit word problem measure to identify students who experienced difficulty with math. So those students were those who performed below the 25th percentile. And so you'll see those students today categorized as MD, or math difficulty. And that is different from math disability, just a note. And then we compared those students to the students that did not have math difficulty. So today you'll see those students abbreviated as TA, or typically achieving. Now, we use the single-digit word problem measure to identify students with and without MD, but then we use this double-digit word problem measure to analyze the word problem performance of these students further. And so that's what we'll share with you here on the following slides. We asked students to solve a variety of double-digit word problems, all falling under the additive category of the additive schema categories. So students solved total problems where parts are put together for a total. This could have included 2 parts put together for a total, or 3 or more parts put together for a total. And on some of the word problems, the total was the unknown, and on some word problems, the part was the unknown. Students also solved difference problems where amounts are compared for a difference. And as you'll see, students had to solve for the unknown greater amount, the unknown lesser amount, or the unknown difference amount. And then students solved change problems where there's an amount that increases or decreases. And on these change problems, students may have solved for a start that's unknown, a change amount that is unknown, or an end amount that is unknown. So first, we're going to look at the measure that all of the students solved. So both typically achieving students and students with math difficulty. And then we'll look at a measure that's fairly similar that only the students with math difficulty solved. So here, all students, all 2,800 students, answered these 8 word problems. So for this assessment, we only had 1 total problem, and here it was an unknown part. We did not include a total problem with an unknown total because those are the easiest for students to solve, and we didn't feel that it was worth our time to include that on this measure. Students solved 3 difference problems on this measure, and you can see problem B has a greater amount missing, problem G has the lesser amount missing, and problem E has the difference missing. And then students solved 2 change increase problems, one with an end amount missing and one with the start amount missing. And they solved 2 change decrease problems, one with an unknown start and one with an unknown change. If we think about the variations in additive problems, there are 11 altogether, and here we only have 8 problems. So one of the things that we will talk about in our work is that we did not survey each of the different variations of these additive word problems equally. So we have a little bit of a limitation there in terms of only asking students to solve 8 variations of additive problems instead of 11. So I'm going to turn it over to Tessa, who's going to talk us through the results from what happened when we compared the typically achieving students to the students with math difficulty.
All right, so first we will look at the typically achieving students. And for these students, the change increase problems with the end and the change decrease problem with the change unknown were the easiest for them to solve. They also performed high on the difference problems with the unknown or with the greater, and the unknown with the lesser amounts, a lesser amount unknown. Then the two change problems that had the start amount unknown were slightly more challenging with than the total problem with the part unknown, even more challenging. And then the students performed the lowest on the difference problem with the unknown difference. And we were looking at that, and that what problem also includes some irrelevant information, which could have been an added complication. So the students with MD performed similarly in relation to how which problems were the most challenging to the least challenging. So the change increase with the end unknown, the change decrease with the change unknown, and the difference with the greater unknown were the three most easiest for them to solve, but it was slightly different with the difference problem slightly easier than the two change problems. Then after that, the change decrease with the unknown start was the next most challenging, with then the difference problems and the other change increase with the start unknown to be slightly more challenging. And then with the total with the part unknown and the difference with the unknown difference as the most challenging, similar to the typically achieving students. Also, as a note for the students with MD, all problems were more difficult. They had more difficulty on all problems than the typically achieving students.
And then we'll share some data on this word problem measure that we only administered to the students with MD. And we're not going to show you the measure now, but we'll just show you the results from that. So Tessa, take it away.
Okay, so for this one, the change decrease problems with the change and n unknown were the easiest for them to solve. Then came the difference with the unknown, the greater amount, and then the change decrease with the start amount unknown, and then change increase with the end unknown. And then the difference problem with the unknown at the lesser amount, and then the most challenging was the total with the part unknown. So this pattern was similar to what we were seeing in the previous assessment, where that total with the part unknown was on the more challenging side, while those change problems with the end and change amount were more on the easier side for students to solve. And then came the problems with the graphs and charts were actually a little bit more challenging for students with MD, despite the type of schema that they had. So that was, we have two charts and graph problems here, and then we have another three that were the most challenging for students to solve. And as you can see, most of three of these most challenging 6 problems were total with a part unknown.
And so what we saw overall for the typical achieving students when we compared them to the students with math difficulty, we saw that overall change and difference problems seemed easier for students than total problems. Do note in that comparison, we only had one total problem, and that was a total problem with an unknown part. And so in the future, we would suggest having more than one total problem, or at least several different total problems that students have to solve. And the other thing that we noted, as Tessa said, is that the typical achieving students outperformed the students with math difficulty on every word problem. And we tested that difference, and across all 8 problems, it was a significant advantage for the students who did not experience math difficulty. Probably not a surprise because our screener identified students with math difficulty based on single-digit word problem performance, but we saw that those differences persisted on double-digit word problems as well. Now, for the students with math difficulty, we saw the same pattern where change and difference problems on average were easier than total problems. Most of our total problems that the students with math difficulty answered were those total problems with a part unknown, and those seem particularly challenging, especially when the information is embedded within a charter graph. On this assessment, we had word problems that did have irrelevant information in some of them. And on average, the students with math difficulty performed lower on the word problems that did include irrelevant information. So we would include that irrelevant information makes these word problems more difficult. And we also noted that all of the problems with charts and graphs, students with math difficulty had a very difficult time solving correctly. So those charts and graphs makes problems more difficult, and many times a chart or graph has extra information in it. So it actually has irrelevant information in the chart or graph instead of in the text-based scenario. And so we need to work with students to help them understand how to interpret that chart or graph and what information from the chart or graph do you need to solve the problem correctly. So our considerations for research are the following. So we would like to have a more fair assessment of word problem solving with all of the variations that students would see in additive word problems. And there are 11 of those variations. And if we wanted to ask students to solve at least 2 of each of those variations, that would be a 22 word problem test. And for us, we typically give students about 2 to 3 minutes to solve each problem. And so you can see why we've not included all of those variations and had multiple versions of each variation, because it would just be a very long assessment that we might ask students to do. And we don't want to tax students to do a 60-minute word problem assessment when we can get a pretty good understanding of their word problem assessment with just those 8 problems. But we would suggest for research that we do need to also test more consistency with the numbers that are presented in the word problems and maybe the scenarios and the names. So maybe trying to keep those things constant while only varying the schema to then really try to isolate whether the student struggles with the schema or whether there are extra things in the problem that cause difficulty for students. So I think there's a lot of really unique things that we could do in terms of research to help understand what's going on in terms of word problem performance. And then in terms of practice, our primary conclusion is that students with math difficulty probably need extra word problem intervention and word problem support. But if you kind of go back to the typical achieving students, we saw that their average response rate for correct responses was anywhere from about 20 to 70%. So that means that many of these students who are typically achieving are also having difficulty with these word problems. And so it's likely that more targeted word problem practice for all students is necessary, but for students with math difficulty, it's absolutely essential. So I'll pause there and open it up to any questions. Gabriella. Hold on, I can't hear you, Gabriella. Maybe give it a try now. Oh, I'm still having a hard time. We'll go to Hans and then we'll come back to you, Gabriella.
I hope I do not ask the same question that Gabriella wanted to ask.
Well, maybe great minds think alike there, Hans.
So I was referring to your last comment about consistency. I mean, of course it was too short, but when skimming over the problems you presented, it seemed to me that the one with lower accuracy were often lexically inconsistent.
Yeah. Well,
did you have a look at that?
Yeah, we haven't looked at like the lexical complexity. We draw all of these word problems from released items that have been released here in our state of Texas or elsewhere in the United States. And so we're trying to put together word problems that we know that like we didn't create, but that students would actually be be setting up and solving in textbooks and on high stakes exams. And so for that reason, we haven't really thought about the lexical complexity of these word problems. More often, we're kind of matching them to other word problems that we've seen out there in the world. But I think that from a research perspective, we could do a better job, or just have a different study where we do try to account for all of those different complexities that go into the word problem.
Yeah, and the follow-up question, because it's in some literature, it's said when you have these keywords which are either like consistent or inconsistent, that poorer students use shortcuts. So basically they see more and then they do addition. So and you would see that in your data that first in the kind of errors they make, you know, that they, for instance, do addition instead of subtraction, or subtraction instead of addition in some of these problems. So you would see that they use this wrong operation. And second, I don't know if you have reaction times, but sometimes you see in this and you might see in this condition the paradoxical effect that the children with mass disabilities might be actually faster because they use this shortcut. You know, they don't build up the scheme. They see, oh, more, I have to do addition, and then they're fast and incorrect because the shortcut is misleading them in the lexically inconsistent trials.
You're exactly right, Hans. Anecdotally, Tessa has been doing a lot of testing, post-testing lately, and she can attest that many of our students that do have math difficulty, they typically, we kind of describe them as number pluckers, where they take the numbers and they most often just add them together, and then they move on and they're ready to go to the next problem. Whereas students who are really kind of like, you know, diving deeper into the word problem process, they take a longer time to solve those problems. And you're exactly right about the keyword stuff. We just produced a paper about how keywords are pretty ineffective in multi-step word problems. They only work 10% of the time. So I'm happy to share that with you if you're interested.
Oh yeah, I would be delighted. Thank you.
Gabriella. I'm still having a hard time hearing you, Gabriella. Maybe you can type it in the chat there. So
okay.
Yeah.
I type.
There you go. I can hear you now. There you go.
No, you can hear. Okay, fantastic. So my question was, you have a lot of data. Do you have also data on children who are performing the best? So the upper 20%, do they have problems with anything? Or this would be also very interesting. So there is so few things on it.
We have a ton of data on these kids. So for all of the 2,800 students, not only do we have their single digit and double digit word problem performance, we also have their computation performance as measured by the RAT5. We have their equation solving, which gets back to the equivalence stuff that was talked about earlier today, how they solve standard and non-standard equations. And then we also have a test on their understanding of the equal sign. We are doing an error analysis right now on when students don't answer these word problems correctly, what are the errors that they make, but it's not finished just yet. But if you ever want to dig deep into this data, we're pretty much finished with this project and just doing some of these secondary analyses at this point. So we'd love to continue the conversation.
Okay, thank you.
Thank you, Sarah and Tessa. It was really interesting. Is there any other question for any of us? Okay, I don't think so. Shall I close, or Andrea? Okay, I will close. Thank you so much for joining us, and thank you for you presenters. All of the presentations were really interesting. Okay, hope to see you next time. Thank you. Have a good weekend.